Alright, cosmic voyagers, pull up a patch of cosmic dust and get comfortable. Or, just sink deeper into whatever terrestrial bedding you've currently commandeered. Tonight, we're not venturing out to the farthest, most unpronounceable nebulae, nor are we going to try and count the angels dancing on the head of a pin, a notoriously frustrating endeavor, by the way, especially when the angels keep complaining about the lack of legroom. No, tonight we're looking a little closer to home. Much closer. We're going to cast our weary, screen-strained eyes towards that familiar, silvery sentinel that graces our night sky, our moon. The moon. Our constant companion. The silent confidant of lovers, lunatics, and insomniacs alike. The celestial cue for werewolves to get their howl on, and for poets to spill ink in its ethereal glow. It's been up there, faithfully orbiting our little blue marble for a very, very long time. It pulls at our oceans, creating the rhythmic sigh of the tides, a gentle, constant reminder of its gravitational embrace. It might even have helped stabilize Earth's axial tilt, preventing our planet from wobbling around like a drunken top, which, let's be honest, would make seasonal planning an absolute nightmare. Imagine trying to pack for a vacation when summer could flip to Arctic winter in a geological blink. Chaos. So it's there. Familiar. Comforting even. You've seen it 1,000 times, 1,000,000 times. A pale disk, sometimes a delicate sliver, sometimes a blazing orb that washes the landscape in a monochrome dream. But have you ever truly, deeply, let your mind wander into the question of its origin? Not just a casual, oh, it's the moon, but a real head-scratching, furrowed brow contemplation of where this colossal ball of rock actually came from? Because, you see, for something so apparently straightforward, so reliably present, the story of the moon's birth was, for a very long time, one of science's most perplexing cosmic whodunits. A mystery that had some of the finest minds twisting themselves into intellectual pretzels, proposing theories that ranged from the surprisingly elegant to the, well, let's just say wonderfully imaginative, and leave it at that for now. It's a tale that highlights not just the ingenuity of human thought, but also our remarkable capacity for being spectacularly, confidently wrong before, just maybe, stumbling upon something that looks like the truth. And even then, the universe has a habit of smirking and whispering, "Are you sure about that?" Tonight, we're not just going to gaze at the moon, we're going to peel back the layers of its ancient, cratered skin, metaphorically speaking, of course. We're going to journey through the history of our attempts to understand its genesis, exploring ideas that once seemed plausible, even revolutionary, before being quietly, or sometimes not so quietly, ushered off the scientific stage. And then we'll arrive at the current frontrunner, the theory that most scientists nod along to, a story of such staggering violence and cosmic drama that it makes most disaster movies look like a gentle afternoon tea. Think of it as a bedtime story, yes, but one with a bit of a twist. Less, once upon a time in a peaceful meadow, and more, once upon a time in a ferociously chaotic young solar system where things routinely smashed into each other with unimaginable force. Relaxing, right? The universe, in its infinite wisdom, or perhaps its infinite indifference, doesn't really do gentle births for things like moons. It's more of a trial by fire, and then maybe more fire, and then some catastrophic impacts for good measure kind of approach. So let your mind drift. Let the daily anxieties, the unanswered emails, the existential dread about whether you left the stove on, you probably didn't, but the universe is full of unpredictable events, just fade. We're stepping into a realm of colossal scales and ancient timelines, where our everyday concerns shrink into the almost comical insignificance they truly deserve. The moon. It hangs up there, doesn't it? So serene. So lunar. It's seen civilizations rise and fall. It's watched continents drift and dinosaurs roam and then, well, not roam. It's been the silent, impartial observer of every human triumph and every human folly. And for most of that time, we just looked up and wondered. Perhaps we worshipped it, perhaps we navigated by it, perhaps we just used its gentle light to avoid tripping over things in the dark. The idea of truly knowing its origin story was beyond our wildest imaginings. But humanity, for all its flaws, and believe me, the universe has a long, itemized list, is a curious species. We poke, we prod, we can't leave well enough alone. And that big, beautiful, baffling ball of rock was just too tempting a mystery to ignore forever. The quest to understand where our moon came from is a testament to that relentless curiosity, a journey paved with brilliant insights, spectacular misdirections, and the quiet, humbling realization that the cosmos is far stranger, and often far more brutal, than our initial, rather quaint, assumptions. So breathe deeply. Let the weight of the day settle. We're about to embark on a gentle drift through scientific history, a detective story written in stardust and impact craters. Don't worry about understanding every detail. Just let the images form, let the ideas float by. The answers, when they came, were not whispered on a gentle cosmic breeze. They were forged in cataclysm. And yet, from that ancient violence, came the serene, silent companion that watches over your sleep tonight. Funny how the universe works, isn't it? Or perhaps not funny, haha, but funny in that slightly unsettling, well, that's unexpectedly grim yet strangely beautiful kind of way. Prepare for a story that might just make you look at that familiar face in the sky a little differently. As we begin to drift back further and further before the sleek rockets and the sophisticated computer models, before we even had a decent telescope, the moon was already there, wasn't it? A constant, shimmering puzzle. And the question of its origin wasn't just a casual curiosity, it was a profound headache, a real cosmic conundrum for those who dared to ponder it. Why was it so tricky? Why did this seemingly straightforward celestial neighbor guard its birth certificate with such obstinate secrecy? Well, for starters, the moon is odd. It's not just any old space rock that happened to get snagged by Earth's gravity. It's big. Really big relative to its parent planet. Most moons in our solar system are pipsqueaks compared to the planets they orbit. Jupiter and Saturn, those gas giant behemoths, have veritable entourages of moons, some quite large, yes, but none that rival the Earth-moon size ratio. Our moon is more than a quarter the diameter of Earth. Imagine if you had a pet dog that was a quarter of your height and mass. You wouldn't just call it a pet, you'd call it a roommate, possibly a slightly intimidating one. This sheer size suggested a connection, a shared history, that was more intimate than a mere casual acquaintance. It hinted at something dramatic. Then there's the moon's composition. When scientists finally got their hands on actual moon rocks, precious souvenirs brought back by the Apollo astronauts, a feat that still boggles the mind if you think about the sheer audacity of it, popping over to another world and bringing back bits of it like geological holiday snaps, they found some intriguing similarities to Earth's rocks. The oxygen isotopes, for instance, which are like a chemical fingerprint for planetary bodies, were remarkably similar. This suggested they formed from the same primordial stuff, in roughly the same neighborhood of the solar system. So far so good. Perhaps they were siblings, as some early theories would propose. But here's where the universe throws in a curveball, or perhaps a cosmic slider, just to keep things interesting. While some aspects were similar, others were annoyingly different. The moon, it turns out, is a bit of a lightweight. It has a much smaller iron core than Earth does. Earth has a big, dense, molten iron heart, responsible for our protective magnetic field, the very thing that shields us from some of the nastier bits of solar radiation, making life as we know it possible. Without it, we'd be a bit more irradiated and crispy. The moon, however, seems to have skipped leg day, metaphorically speaking, when it came to accumulating heavy metals like iron. This was a major puzzle. If they formed together from the same cloud of dust and gas, why the discrepancy in their core portfolios? It's like two twins where one inherits all the family jewels and the other gets a charming collection of pebbles. Not quite fair and scientifically perplexing. Furthermore, the moon is bone dry. Not just a bit parched, like your throat after a particularly enthusiastic karaoke session, but cosmically desiccated. Earth is famously a water world, teeming with oceans, rivers, and that persistent damp patch in your basement. The moon, on the other hand, seems to have had all its volatile elements, things like water, sodium, potassium, baked out of it early in its history. This suggested it had experienced some incredibly high temperatures, a trial by celestial fire, perhaps. And then there's the Earth-Moon system's angular momentum. Now don't let your eyes glaze over. Angular momentum is just a fancy way of talking about how much spin energy a system has. The Earth spins on its axis, giving us day and night, and the moon orbits the Earth. Together, they have a surprisingly large amount of angular momentum, more than most other planet-moon systems. This implied that whatever event created the moon must have involved a tremendous amount of energy and a rather specific kind of cosmic choreography. It wasn't just a gentle coming together, it was more like a violent, spinning dance. So, you see the challenge for these early cosmic detectives. They had a suspect, the moon, with a very peculiar set of characteristics. Some clues pointed one way, similar oxygen isotopes, suggesting a close family tie, while others pointed in completely opposite directions, different iron content, lack of volatiles, high angular momentum, suggesting a more complicated, perhaps traumatic, upbringing. It was like trying to assemble a jigsaw puzzle where half the pieces seemed to come from a different box, and the picture on the lid was frustratingly vague, possibly drawn by a toddler with a grudge against straight lines. The tools available were also limited. Early astronomers could observe the moon's orbit, its phases, its surface features through increasingly powerful telescopes. They could measure its mass and density, but they couldn't reach out and touch it. They couldn't analyze its rocks. They were like detectives trying to solve a murder mystery armed only with blurry photographs taken from a great distance, and perhaps a few vague eyewitness accounts from unreliable comets. This difficulty, this inherent trickiness, is what makes the eventual unraveling of the moon's origin story so compelling. It wasn't a simple, aha, moment. It was a slow, arduous process of proposing ideas, testing them against the available evidence, finding them wanting, and then, with a sigh and perhaps a fresh pot of coffee, going back to the drawing board. Each wrong theory, as we'll soon explore, wasn't necessarily a failure. It was a stepping stone, a vital part of the intellectual journey. Each discarded hypothesis helped to narrow down the possibilities, to highlight the specific features that any successful theory would ultimately need to explain. It's a bit like trying to find your way out of a vast, dark labyrinth with only a flickering candle. You take a path that leads to a dead end. You curse the labyrinth designer, probably the same entity who came up with existential dread, backtrack and try another. Each dead end isn't a waste of time, it's information. It tells you where not to go. And slowly, painstakingly, you begin to map the maze. The quest for the moon's origin, then, was a testament to human persistence in the face of cosmic ambiguity. It forced scientists to be more creative, more rigorous, and ultimately more humble. Because the universe, as we keep discovering, rarely conforms to our neat, tidy expectations. It delights in complexity, in paradox, and occasionally, in mind-boggling violence that somehow gives birth to serene beauty. So settle in. The first few paths these cosmic detectives took were quite imaginative. Now, with the stage set, with our cosmic detectives scratching their heads over this rather perplexing lunar roommate, let's delve into the first of the grand and ultimately flawed theories, the fission theory. Picture the scene. It's the late 19th century. Industrial revolutions are chugging along, science is making bold strides, and confidence is high. If we can build steam engines and telegraphs, surely we can figure out where that big shiny thing in the sky came from. Enter George Darwin. Yes, that Darwin family. Son of Charles, the naturalist who rather famously shook up our understanding of life on Earth. George, however, set his sights a little higher, quite literally. He was an astronomer and mathematician, and he had an idea about the moon, an idea that was both dramatic and, at the time, rather compelling. He proposed that the moon was essentially Earth's runaway child. The fission theory, in a nutshell, suggested that in its very early fiery youth, Earth was spinning incredibly fast. Imagine our planet as a molten, rapidly rotating blob, a cosmic centrifuge going into overdrive. So fast, in fact, that a piece of it, a substantial glob of this molten material, simply broke off. It was flung outwards by the sheer centrifugal force, like a cosmic David slinging a molten Goliath, or perhaps more like an overzealous pizza chef spinning dough a little too enthusiastically and a chunk flies off into the celestial kitchen. This ejected blob, still hot and bothered from its dramatic departure, eventually cooled and coalesced to become our moon. It's a rather vivid image, isn't it? Our own planet, in a fit of youthful exuberance, literally birthing its companion. And for a while, this theory had a lot going for it. Firstly, it neatly explained the moon's existence as a large body orbiting Earth. If it came from Earth, its significant size relative to Earth made a certain kind of sense. It wasn't an adopted stranger, it was flesh of our planetary flesh, or rather rock of our planetary rock. Secondly, it seemed to account for the compositional similarities that were starting to be noticed, even before the Apollo samples. If the moon was carved from Earth's mantle, then it should share some of Earth's chemical characteristics. The early observations of the moon's density suggested it was made of lighter, crust-like material, which aligned with the idea that the outer layers of a rapidly spinning proto-Earth would be the first to go bye-bye. And perhaps most picturesquely, the fission theory offered a rather romantic explanation for a very large earthly feature, the Pacific Ocean Basin. The idea, championed by some, was that this vast depression in Earth's crust was the very scar left behind when the moon was torn away. Imagine that. The largest ocean on our planet, a constant reminder of this dramatic cosmic parturition. You could almost see the Earth sighing in relief, well, glad that's over, while the moon, now a separate entity, began its lonely vigil. It's the kind of grand, sweeping narrative that appeals to our love of a good story, especially one involving planetary-scale drama. So, for a time, the fission theory was quite the scientific belle of the ball. It was elegant, it was dramatic, and it seemed to tie up several observational loose ends with a neat, albeit rather catastrophically formed, bow. Scientists could visualize it, model it with the mathematics of the day, and it felt right. A family story, albeit a slightly dysfunctional one involving high-speed rotation and bits of planets flying off into space. One can imagine astronomers of the era, perhaps with a pipe and a thoughtful expression, nodding sagely and saying, "Yes, flung from the Earth. Makes perfect sense. Another sherry old boy?" However, like many compelling stories that sound great over a late-night brandy, the fission theory started to unravel when subjected to closer scrutiny and more sophisticated calculations. The universe, alas, has a rather annoying habit of letting pesky things like physics get in the way of a perfectly good narrative. One of the biggest problems was the required spin rate. For Earth to fling off a moon-sized chunk, it would have had to be rotating at an absolutely terrifying speed. Something like once every 2.5 hours. Think about that. A day lasting just 2.5 hours. The sun would whip across the sky. You'd barely have time for breakfast before it was time for bed again. More importantly, physicists couldn't figure out a plausible way for Earth to have acquired that much angular momentum in the first place, nor how it would have conveniently slowed down to its current, more leisurely 24-hour spin after the moon's dramatic exit. The cosmic breaks just weren't there. Then, as our understanding of lunar composition improved, particularly with the Apollo samples, more cracks appeared. While there were similarities, the moon wasn't an exact match for Earth's mantle. There were subtle but significant differences in certain elements. If it was just a chip off the old block, these discrepancies were hard to explain. It was like a child claiming to be yours, but having an entirely different accent and a surprising fondness for foods you've never even heard of. Suspicions would arise. And the Pacific Ocean scar? A lovely idea, very poetic, but plate tectonics, a theory that gained traction much later, provided a far more robust and evidence-based explanation for the formation of ocean basins. The Earth's crust, it turns out, is a much more dynamic and restless thing than a mere scab from a lunar birth. The timing didn't quite work out either. The Pacific Basin is much younger than the moon. So, that picturesque scar turned out to be more of a geological red herring. Finally, the moon's orbit was a sticking point. The current orbit of the moon, tilted as it is relative to Earth's equator, is difficult to achieve if it was simply flung off from an equatorial bulge. The mechanics just didn't line up tidily. It's like throwing a ball of dough straight up and expecting it to start circling your head at a jaunty angle. Possible, perhaps, if you're a cosmic juggler of immense skill, but not the most straightforward outcome. So, the fission theory, for all its initial charm and its evocative imagery of a planet giving birth, slowly faded from favor. It was a bold attempt, a product of its time, and it served an important purpose by stimulating debate and further investigation. It was a beautiful hypothesis, as the saying goes, slain by ugly facts. But don't feel too bad for it. In the grand cosmic drama of scientific understanding, even the theories that end up in the famous wrong ideas pile play a crucial role. They are the ghosts in the machine, reminding us that the path to knowledge is often paved with magnificent, instructive missteps. And the idea of Earth itself spinning off a celestial child. Well, it's certainly a more dramatic bedtime image than simply accreting from dust, isn't it? Even if it's wrong, it's wonderfully, cosmically wrong. Alright, so Earth didn't exactly spin itself into a frenzy and pop out the moon like a cosmic champagne cork. That particular family drama, while vivid, hit a few too many physical snags. But the cosmic detectives, undeterred, pulled out another file from their cabinet of lunar conjectures. The capture theory. If the moon wasn't born of Earth, perhaps it was adopted? Or, to put a slightly more dramatic and perhaps less consensual spin on it, perhaps it was kidnapped. The capture theory proposed that the moon was once a wandering celestial body, a lonely orphan of the cosmos, drifting through the solar system, minding its own business. Maybe it formed somewhere else entirely, perhaps in a different part of the protoplanetary disk, or maybe it was even an interloper from farther afield. Then, in a stroke of cosmic serendipity, or perhaps a gravitational ambush, it strayed too close to Earth. Our planet, with its not inconsiderable gravitational pull, reached out and snagged this passing wanderer, pulling it into orbit. Voila! Instant moon. This scenario has a certain roguish charm, doesn't it? The idea of our Earth as a kind of celestial pirate, capturing a prize from the void. Or, if you prefer a more romantic angle, perhaps it was a lonely planet finding a companion in the vast emptiness of space. Hey there, little rock, Earth might have murmured gravitationally, lost are you? Why don't you stick around for a few billion years? One of the appealing aspects of the capture theory was its potential to explain some of the differences between Earth and the moon. If the moon formed in a completely different region of the solar system, it would naturally have a different chemical makeup. This could account for why the moon is so depleted in iron and those volatile elements we talked about earlier. If it was born in a drier, hotter part of the solar system, or had its own independent history before meeting Earth, those compositional quirks wouldn't be so puzzling. They wouldn't be family traits, but rather characteristics of a distinct individual with its own backstory. Think of it like this. If your adopted child has different hair color and a different accent, it's not a mystery, it's because they came from somewhere else. The capture theory offered a similar kind of out for the moon's peculiarities. It provided a way to have a moon that was associated with Earth but not derived from it in a way that demanded identical compositions. Furthermore, some of the irregular moons orbiting other planets in our solar system, particularly the smaller, more distant ones around giants like Jupiter and Neptune, are indeed thought to be captured asteroids or comets. So, there was a precedent for this kind of celestial acquisition. If Jupiter could do it, why not a younger, sprightlier Earth? It seemed plausible, at least on the surface. The cosmos is a dynamic place with objects flying hither and thither. Chance encounters, while perhaps not commonplace for massive objects, weren't entirely out of the realm of possibility. However, as with the fission theory, the celestial mechanics of actually capturing something as enormous as the moon proved to be a rather thorny problem. It's not as simple as just rolling out a gravitational welcome mat. Capturing a body the size of our moon is an incredibly delicate and unlikely maneuver. Imagine trying to catch a very large, very fast-moving bowling ball with a very sticky net, while you yourself are also moving. If the moon approached Earth too fast, Earth's gravity wouldn't be able to hold onto it, it would just slingshot past, perhaps exchanging a brief gravitational nod before disappearing back into the cosmic black. Nice try, it might signal, but I've got places to be. If it approached too slowly or at the wrong angle, it would likely crash into Earth, resulting not in a gentle orbiting companion but in a truly cataclysmic impact. A very different kind of story, and one we'll get to, albeit with a twist. For a successful capture, the moon would have had to approach Earth at just the right speed, at just the right angle, and it would have needed some way to shed a significant amount of orbital energy to settle into a stable orbit. This usually requires a third body to gravitationally assist, or perhaps passage through a dense gas cloud that could create drag. Finding such a perfect trifecta of conditions for an object as massive as the moon was statistically improbable. Very, very improbable. Like winning the cosmic lottery, getting struck by lightning, and finding a perfect avocado all on the same day. Then there was the problem of the moon itself. If it were captured, it would likely have a very eccentric or elongated orbit, and perhaps a highly inclined one, not the relatively ordered and nearly circular path it currently enjoys, though it is slowly receding, but that's a tale for another sleepy night. While orbits can change over billions of years due to tidal forces, getting it from a wild, freshly captured trajectory to its current, more sedate path presented another set of complex mechanical challenges. And the biggest nail in the coffin for the simple capture theory once again came from those talkative moon rocks. Remember those oxygen isotopes, the chemical fingerprints that were so similar between Earth and the moon? Well, if the moon formed in a completely different part of the solar system, it should have a different oxygen isotope signature. The fact that they were so uncannily alike was a strong piece of evidence against the moon being a captured alien. It suggested they shared a common nursery, a common source of building materials, which the capture theory in its purest form couldn't easily explain. It would be like discovering your adopted child, who supposedly came from a distant land, has exactly the same rare blood type and peculiar birthmark as you. You'd start to suspect the adoption agency wasn't telling you the whole story. So, the tale of the wandering moon finding a home, or being forcibly detained by Earth's gravitational clutches, while making for a romantic or dramatic narrative, ultimately buckled under the weight of physical improbability and geochemical evidence. It was another fascinating idea, another path explored in the great lunar labyrinth, but it too led to a scientific dead end. The universe, it seemed, wasn't quite ready to give up its secrets with such a straightforward tale of cosmic abduction. The moon's origin story was proving to be a far more intricate and homegrown affair, even if the home was about to get a rude, planet-shattering visitor. But we're getting ahead of ourselves. For now, let's just allow the image of a lonely moon, drifting through the velvet black, to lull us, even if its capture was not to be. Alright, so our Earth didn't spin off the moon in a fit of rotational exuberance, nor did it play the role of a cosmic kidnapper, snatching an unsuspecting wanderer from the void. Both of those narratives, while possessing a certain dramatic flair, crumbled under the stern gaze of physics and the silent testimony of lunar rocks. But the persistent cosmic detectives, ever hopeful, had another hypothesis up their sleeves, one that seemed on the surface far more sensible, almost a bit boring in comparison: the co-formation theory. This idea, also known as the condensation or accretion theory, proposed that Earth and the Moon essentially grew up together, side by side, like celestial siblings. Picture the early solar system, not as a collection of neat, well-defined planets, but as a vast, swirling disk of gas and dust, the protoplanetary disk. Within this cosmic nursery, tiny particles began to clump together due to gravity, a process called accretion. Dust bunnies became pebbles, pebbles became boulders, boulders became planetesimals, and eventually these planetesimals collided and merged to form planets. The co-formation theory suggested that as the proto-Earth was taking shape through this accretion process, a smaller eddy of material, a sort of mini-me cloud of dust and gas, began to coalesce nearby. This secondary clump, caught in Earth's gravitational influence but distinct enough to form its own body, gradually grew into the Moon. They were, in essence, womb mates, gestating in the same region of the solar system from the same parental cloud of primordial material. It's a rather neat and tidy picture, isn't it? No messy flinging of planetary bits, no improbable captures. Just the orderly, almost domestic process of two celestial bodies forming in tandem. This theory had a natural appeal because it seemed so plausible. If planets formed from accretion disks, why couldn't a large moon form alongside its planet in a similar fashion? It felt like a common-sense explanation, the cosmic equivalent of, well, obviously. And it did a decent job of explaining some key features. For instance, the Moon's orbit around Earth, particularly its prograde direction, orbiting in the same direction as Earth's spin, and its relatively low inclination, not tilted too dramatically compared to Earth's orbital plane around the Sun, seemed consistent with forming from the same swirling disk of material. If they were born from the same rotating system, they would naturally share some of its dynamic characteristics. Furthermore, the co-formation theory initially seemed to offer a straightforward explanation for the similar oxygen isotope ratios. If Earth and Moon were built from the same batch of cosmic ingredients, drawn from the same local reservoir in the protoplanetary disk, then it would make perfect sense for their chemical fingerprints to match. They went to the same cosmic grocery store, so to speak, and bought the same brand of oxygen. This idea of a twin birth, of Earth and Moon as companion worlds taking shape together, held sway for a considerable time. It was less dramatic than fission or capture, certainly. No planetary scars, no tales of wandering celestial orphans. Just the quiet, patient work of gravity, slowly building two worlds in close proximity. It's the kind of story that doesn't make for thrilling blockbuster movies, perhaps, but it has the reassuring feel of something orderly and understandable. You could almost imagine the young Earth and proto-Moon side by side, nudging each other occasionally as they swept up the remaining debris in their shared orbital space. Mind if I take this asteroid? One might signal to the other. Be my guest, I'm still working on this cloud of pebbles. However, like a seemingly perfect alibi that starts to look a bit shaky under cross-examination, the co-formation theory began to encounter some significant problems as scientists gathered more data and refined their models. The universe, it seems, rarely opts for the most boring explanation when a more spectacularly violent one will do. One of the major stumbling blocks was, once again, the Moon's small iron core. If Earth and Moon formed from the same undifferentiated blob of material, why did Earth hog all the iron? Accretion models suggested that both bodies should have incorporated a similar proportion of heavy elements relative to their total mass. It was hard to get a scenario where Earth built up its substantial iron core while its next-door neighbor, forming from the same stuff, ended up so iron poor. It's like making two cakes from the same batter, and one ends up rich and chocolatey, while the other is mysteriously missing most of its cocoa. You'd suspect some preferential sifting was going on, and the co-formation theory didn't offer a convincing mechanism for this celestial segregation of metals. Then there was the issue of the Earth-Moon system's high angular momentum. We talked about this before. The combined spin and orbital energy is unusually large. While co-formation could explain the direction of the orbit, it struggled to account for the sheer amount of this angular momentum. Simple, side-by-side accretion from a disk doesn't naturally lead to such a dynamically hot system. It would be like two ice skaters gently joining hands and then spontaneously starting to spin at breakneck speed. Something extra, some energetic kick, seemed to be missing from the co-formation recipe. And while the similar oxygen isotopes were a point in its favor, other compositional differences, like the Moon's striking lack of volatile elements, water, sodium, etc., were harder to reconcile if they both just condensed quietly from the same cloud. Why would one sibling be thoroughly baked dry while the other retained its volatiles? One might argue that the smaller moon lost its volatiles more easily due to lower gravity and proximity to the sun, but the degree of depletion was extreme, hinting at a more traumatic heating event than simple, gentle accretion would provide. So, the co-formation theory, despite its initial appeal of simplicity and plausibility, found itself increasingly unable to explain all the quirky characteristics of our lunar companion. It was like a suspect whose alibi seemed solid. I was at home, quietly accreting. But the forensic evidence, the iron discrepancy, the missing volatiles, the excessive spin, just didn't quite add up. The moon was clearly trying to tell us something more dramatic about its origins. This theory, like the fission and capture theories before it, served its purpose. It highlighted what couldn't easily be explained by a straightforward, tandem formation. It pushed scientists to look for a process that could account for the high angular momentum, the iron deficiency, and the volatile depletion, all while preserving those telltale oxygen isotope similarities. The cosmic detectives were getting closer. The clues were piling up. The stage was being set for a theory that was less about gentle sibling rivalry and more about a catastrophic, world-altering event. The quiet, domestic scene of co-formation was about to be shattered by a far more violent, and ultimately more compelling narrative. The universe, it seemed, was in the mood for some fireworks. So, our cosmic investigators had explored a few promising avenues, each with its own allure, each ultimately leading to a frustrating dead end. Earth hadn't flung off the moon, nor had it nabbed a passing cosmic vagabond, and the idea of them growing up as placid, side-by-side twins just didn't quite hold water, or rather didn't hold iron in the moon's case. The lunar enigma persisted. What was needed was a breakthrough, a new piece of evidence so compelling that it could slice through the Gordian knot of conflicting clues. And that breakthrough came not from ever more powerful telescopes peering from Earth, but from a series of audacious voyages that took humanity quite literally to another world. Enter the Apollo program. Between 1969 and 1972, a handful of remarkably brave, or perhaps gloriously foolhardy, individuals strapped themselves to the top of colossal rockets and journeyed across 250,000 miles of cold, indifferent space to walk upon the surface of the moon. It remains one of humanity's most astonishing achievements, a testament to ingenuity, courage, and an almost absurd level of ambition. Let's go to the moon. Sure, why not? Pass the slide rule. But beyond the iconic footprints and the fluttering flags, which by the way only fluttered because they had a telescopic pole along the top edge, no atmosphere, no breeze, a lovely little detail of stark lunar reality, the Apollo astronauts were on a scientific mission. They were geological prospectors on a new frontier. And they brought back treasure. Not gold or diamonds, but something far more valuable to the cosmic detectives puzzling over the moon's origin: rocks. Lunar samples. Hundreds of kilograms of them. Basalts, anorthosites, breccias, bits and pieces of the moon itself, carefully collected, catalogued, and transported back to Earth for intense scientific scrutiny. These weren't just any old rocks. These were time capsules, silent witnesses to the moon's ancient history, its formation, and its evolution. Suddenly, scientists weren't just relying on remote observations and theoretical models. They had tangible pieces of the puzzle in their laboratories. They could analyze their chemical composition with unprecedented accuracy, determine their ages, study their mineralogy, and subject them to all manner of sophisticated tests. It was as if, after centuries of trying to diagnose a patient from across a crowded room, the doctors were finally allowed to take a blood sample. And these moon rocks began to talk. Or rather, they began to yield their secrets under the probing eyes of geochemists and petrologists. And what they revealed threw several of the prevailing theories into serious disarray, while simultaneously pointing towards a new, more violent, and ultimately more satisfying explanation. One of the first major revelations confirmed by the Apollo samples was the striking similarity in oxygen isotope ratios between Earth and the Moon. We've touched on this before, but having actual lunar material to compare directly with terrestrial rocks made this finding undeniable. This wasn't just a general similarity, it was a remarkably precise match, suggesting that the Earth and the material that formed the Moon shared a common reservoir of primordial material. This was a huge clue. It strongly implied that the Moon wasn't a captured alien from some distant part of the solar system with its own distinct isotopic signature. It had to have a very intimate connection to the Earth's building blocks. However, the rocks also confirmed in stark detail the Moon's peculiar compositional quirks. They were indeed significantly depleted in volatile elements, water, sodium, potassium, lead, compared to Earth rocks. It was as if the Moon had been systematically baked, stripped of anything that could easily vaporize. This pointed to an incredibly high-temperature event in its formation, far hotter than would be expected from simple co-accretion. The moon, it seemed, had been through hell, or at least a celestial inferno. Furthermore, analysis of the lunar crust, particularly the abundance of a type of rock called anorthosite, led to a fascinating conclusion. The early moon was likely covered by a vast, deep ocean of molten rock, a magma ocean. The lighter anorthositic rocks would have crystallized and floated to the top of this magma ocean, forming the primordial lunar highlands. For such a massive magma ocean to exist, an immense amount of energy must have been involved in the moon's formation. Gentle accretion or capture just wouldn't cut it. This was evidence of a truly cataclysmic birth. And then there was the iron. The samples confirmed the moon's overall low density and thus its relatively small iron core. This was a critical piece of the puzzle. Any successful theory of lunar origin would have to explain how the moon ended up so iron-poor compared to its much more iron-rich planetary neighbor, Earth, especially if they shared the same oxygen isotopes. The fission theory had tried, suggesting the moon came from Earth's iron-poor mantle, but it had its own insurmountable problems. Co-formation couldn't explain it. Capture couldn't reliably explain it while also matching the isotopes. So, the Apollo samples, these precious pieces of another world, effectively closed the case on some of the older, simpler theories. They provided a wealth of hard data that any new hypothesis would have to contend with. They painted a picture of a moon born from the same stuff as Earth, yet subjected to extreme temperatures and strangely deficient in iron. It was like finding out your long-lost sibling shares your DNA, but was apparently raised in a blast furnace and put on a strict no-iron diet. Highly unusual and demanding a rather extraordinary explanation. The scientific community was abuzz. The old models were creaking under the strain of this new evidence. The clues were pointing towards something big, something energetic, something messy. The quiet, orderly nursery of the co-formation theory was clearly not where the moon was born. The moon rocks were whispering of fire, of impact, of a scale of violence that was, until then, difficult to fully comprehend. It's a wonderful irony, isn't it? Humanity reaches out, touches another world, brings back a few handfuls of dust and rock, and in doing so, completely rewrites the story of our closest celestial companion. It's a testament to the power of empirical evidence, of actually going and seeing and collecting. Those silent, gray stones, gathered from a desolate, airless landscape, held the key. They were the star witnesses, and their testimony was about to blow the case wide open, paving the way for a theory that involved a collision of truly epic proportions. The stage was set for a new protagonist, or perhaps antagonist, to enter the story. A phantom planet whose sacrifice gave birth to our moon. The courtroom of cosmic theories was in a bit of an uproar. The fission theory had been discredited due to impossible physics. The capture theory, while romantic, was a statistical long shot with isotopic mismatches. The co-formation theory, so sensible on the surface, couldn't account for the moon's missing iron heart or its baked dry nature. The moon rocks, brought back by the heroic and probably slightly dusty Apollo astronauts, had acted as star witnesses, systematically dismantling the existing alibis. The pressure was on. Science needed a new suspect, a new narrative, one that could accommodate all these perplexing, seemingly contradictory clues. The shared oxygen isotopes, the missing iron, the volatile depletion, the evidence of a magma ocean, and the Earth-Moon system's high angular momentum. It was in this climate of scientific anticipation, in the mid-1970s, that two separate groups of scientists, working independently, William Hartmann and Donald Davis in one group, and Alastair Cameron and William Ward in the other, converged on a startling yet remarkably compelling idea. It wasn't a gentle birth, nor a sly capture, nor a quiet co-formation. No, the moon, they proposed, was born from a catastrophe of almost unimaginable scale. It was the result of a truly monumental cosmic smash-up. This, my friends, is the dawn of the giant impact hypothesis. Imagine the scene. The early solar system, a far more chaotic and crowded place than it is today. It wasn't the orderly, well-spaced arrangement of planets we now see. Instead, it was more like a demolition derby with numerous planetesimals and protoplanets, worlds in the making, zipping around, their orbits still settling occasionally and catastrophically, crossing paths. Our own proto-Earth, still glowing hot from its own accretion, was one of these nascent worlds. And then into this cosmic mosh pit came another player. A protoplanet roughly the size of Mars. Not a trivial little asteroid, mind you, but a substantial world in its own right. This celestial wanderer, later poetically and somewhat ominously named Theia, after the Titan goddess in Greek mythology who was the mother of Selene, the goddess of the moon, a rather fitting if ultimately tragic appellation, was on a collision course with the young Earth. The giant impact hypothesis posits that Theia didn't just nudge the proto-Earth or give it a glancing blow. No, this was a full-blown, planet-shattering collision. Theia struck the proto-Earth with incredible violence, likely at an oblique angle. The energy released in this impact would have been staggering, beyond anything we can truly comprehend. Think of every nuclear weapon ever built on Earth detonating simultaneously, and then multiply that by a factor of millions or even billions. It was an event that would have fundamentally reshaped both colliding bodies. The impact would have been so immense that it would have vaporized a significant portion of Theia and a large chunk of the proto-Earth's mantle. The cores of the two bodies, Theia's smaller iron core and Earth's larger one, likely merged, with a denser material from Theia sinking towards the center of the now even larger Earth. This is a crucial point, as we'll see. But what about the rest? The vaporized rock, the molten debris, the shattered remnants of Theia's mantle and the upper layers of Earth's mantle. This incandescent, superheated material wouldn't just disappear. It would have been blasted outwards, ejected into orbit around the traumatized, reshaped Earth. Imagine a colossal ring of fire and rock, a glowing, swirling halo of debris encircling our planet. This wasn't the serene, silvery moon we see today. This was a hellish, chaotic disk of raw material hot enough to melt rock, seething with energy. And from this disk of debris, the giant impact hypothesis suggests, our moon began to form. Over a relatively short timescale, perhaps just a few years or decades or centuries, a mere blink in cosmic terms, the material in this ring started to clump together. Gravity, ever patient, ever persistent, began to pull these fragments towards each other. Smaller clumps merged to form larger ones, and eventually, through this process of accretion from the impact-generated disk, a single large body emerged. The moon. This was a radical idea. It replaced the gentle, almost pastoral notions of lunar formation with a vision of unimaginable violence and cosmic rebirth. It wasn't a story of quiet creation, but of spectacular destruction leading to a new creation. It was, in essence, a planetary-scale car crash, with our moon being the beautifully formed, albeit slightly dented and traumatized, fender that got thrown clear. The beauty of the giant impact hypothesis, however, wasn't just in its dramatic imagery. It was in its astonishing ability to explain, with a single, sweeping event, many of the puzzling characteristics of the moon that had stumped previous theories. Suddenly, the moon's small iron core made sense. If Theia's iron core merged with Earth's during the collision, and the moon formed primarily from the ejected mantle material of both Theia and Earth, which is naturally lower in iron, then the moon would end up iron poor. The heavy lifting of core formation had already been done, and the lighter, rocky debris got to form the new satellite. The volatile depletion? A massive, high-energy impact that vaporized rock would certainly drive off volatile elements. The moon literally condensed from a superheated cloud of silicate vapor. Anything easily turned to gas would have been lost to space. The moon was born in a cosmic furnace. The magma ocean? The sheer energy of the impact and the subsequent accretion of hot debris would have easily been enough to melt the outer layers of the newly forming moon, creating that vast ocean of molten rock that the Apollo samples hinted at. The moon started its life as a glowing ball of lava. And the Earth-Moon system's high angular momentum? An oblique, off-center impact by a Mars-sized body would be an incredibly effective way to impart a huge amount of spin to the Earth-Moon system. The glancing blow would send things whirling, setting up the dynamical conditions we observe today. Even the oxygen isotope similarity could be accommodated. If the moon formed largely from material ejected from Earth's mantle, mixed with material from Theia, which, having formed in a similar region of the solar system, might have had a similar isotopic signature to begin with, or perhaps the intense mixing during the impact homogenized the material, then the isotopic match was no longer a mystery. They were, in a very real sense, made of the same or at least thoroughly blended stuff. It was elegant. It was powerful. It was, dare I say, almost beautiful in its destructive creativity. The giant impact hypothesis wasn't just another guess. It was a comprehensive explanation that tied together disparate threads of evidence into a cohesive and compelling narrative. It was a revelation born from catastrophe, a story of two worlds dying to give birth to the Earth-Moon system we know today. A truly smashing idea in every sense of the word. And as we drift deeper into this cosmic bedtime story, we'll explore just how this giant impactor, this Theia, played its fateful, sacrificial role. So we have our culprit, or perhaps our sacrificial lamb in this grand cosmic drama. Theia. This isn't just a placeholder name for some anonymous celestial body. it represents a real physical object, a protoplanet with its own history, its own journey through the chaotic youth of our solar system, a journey that was destined to end in a spectacular moon-birthing finale. Let's try to imagine this doomed world, this Theia, in the time leading up to its fateful rendezvous with the proto-Earth. Visualizing Theia isn't like picturing Mars today, with its reddish dust and polar ice caps. This was much earlier, around 4.5 billion years ago. Theia would have been a young world, still hot from its own formation through the accretion of smaller planetesimals. It was likely a differentiated body, meaning that heavier elements like iron and nickel would have already sunk to its center to form a metallic core, while lighter, silicate materials would have formed its mantle and crust. A world in its own right, with its own geology, its own internal heat, perhaps even the very beginnings of a primitive atmosphere, though that's purely speculative. Size-wise, as we mentioned, it's generally thought to have been comparable to Mars. That means a diameter of roughly half that of Earth. Not a trivial piece of cosmic shrapnel, but a significant planetary player. It would have had its own gravity, enough to pull it into a spherical shape. It would have been orbiting the young sun, likely in a path that, for a long time, was stable and unremarkable, or at least, not immediately threatening to the proto-Earth. Imagine Theia drifting through the primordial solar system. It would have been a desolate, fiery landscape. Impacts from smaller debris would have been frequent, scarring its surface, contributing to its internal heat. Perhaps it had a mottled appearance, a mix of darker, solidified lava flows and lighter, older crustal materials. It wouldn't have been a welcoming place for life as we know it, far too hot, too violent, its atmosphere, if any, likely thick with volcanic outgassings and the remnants of vaporized impactors. A truly primordial world, raw and untamed. Its journey towards the proto-Earth wasn't a sudden, unexpected swerve. Planetary orbits, especially in the early, crowded solar system, could be nudged and perturbed by the gravitational influence of other large bodies, like the gas giants Jupiter and Saturn, or even other Mars-sized protoplanets. It's thought that Theia might have formed in a relatively stable Trojan point of Earth's orbit, either leading or trailing Earth by about 60 degrees, held in a gravitational sweet spot. However, even these points aren't perfectly stable forever, especially if other planets are migrating or if the protoplanet grows too large. Eventually, something disturbed Theia's orbit. Perhaps it was a gravitational nudge from Jupiter, or perhaps it grew massive enough that its own gravitational interactions with the proto-Earth became unstable. Slowly, almost imperceptibly at first, its orbit would have begun to shift, to elongate, to become more eccentric. The dance between Theia and the proto-Earth, once perhaps a distant, respectful waltz, began to tighten into something more dangerous, more intimate. Computer simulations, the modern-day crystal balls of astrophysicists, have modeled these interactions. They show how, over timescales of potentially millions of years, Theia's orbit could have become increasingly chaotic, eventually leading it onto a direct collision course with our own nascent planet. There's a certain melancholy beauty in picturing Theia during this time, isn't there? A substantial world, forged from the same stardust that made Earth, pursuing its own cosmic destiny, blissfully unaware, because planets, alas, are not sentient, despite our tendency to personify them of the cataclysmic role it was about to play. It was simply following the inexorable laws of physics, its path dictated by gravity and momentum. It wasn't evil, it wasn't malicious, it was just in the wrong place at the wrong time, or perhaps, from the moon's perspective, exactly the right place at the right time. One can imagine the sky of the proto-Earth, in the millennia leading up to the impact. Perhaps Theia would have become visible, first as a faint, star-like point, then gradually growing larger, night after night, week after week. A new, ominous presence in the heavens. Did any primitive, prelunar organisms, if any existed on Earth at that incredibly early stage, look up and sense the impending doom? Probably not. But it's a chilling thought nonetheless. A silent, growing threat, looming larger in the primordial sky. Theia was, in essence, a cosmic sacrifice. Its destruction was necessary for the creation of the Earth-Moon system as we know it. Without Theia, or something very much like it, we wouldn't have our large moon with all its stabilizing influences and its nightly glow. Our planet might be a very different place, perhaps spinning faster with a more chaotic tilt, more extreme seasons, or no significant tides. Life, if it arose at all, might have taken a very different path. So, Theia isn't just a footnote in astronomical history, it's a crucial, if tragic, character in our planet's origin story. Its existence, its composition, its size, and its ultimate demise are all key parameters in the giant impact hypothesis. Scientists continue to refine models of Theia, trying to understand its precise characteristics to better match the chemical and isotopic signatures found in Earth and Moon rocks. Was it wetter or drier than the proto-Earth? Did it form closer to the Sun or further away before its fateful orbital migration? These are questions that researchers still grapple with, using sophisticated simulations and geochemical analysis. But the core image remains: a Mars-sized world, a sibling planet forged in the same cosmic crucible as Earth, set on an unavoidable path to a collision that would tear it apart, merge its heart with ours, and scatter its rocky remains to form our beautiful, enigmatic moon. It's a stark reminder that the universe is not a gentle, nurturing place. Creation often arises from destruction. Order emerges from chaos. And sometimes, for a system as unique and precious as our Earth and Moon to exist, another world has to die. A rather sobering thought to drift off to sleep with, but also a profound one. Theia, the lost mother of our moon, a silent ghost in the history of our solar system, forever imprinted in the very fabric of the world beneath our feet and the silver orb above our heads. Now let us linger, if you will, on that truly terrible world-altering day. Or perhaps day is too mundane a word for an event of this magnitude, an event that unfolded over hours, reshaping planets and birthing a moon. Let's try to imagine, as best our human minds can grapple with such cosmic violence, the moment of impact, the day the proto-Earth and the Mars-sized Theia collided. This isn't a gentle nudge, not a fender bender on the celestial highway. This is planetary annihilation and rebirth, all rolled into one cataclysmic instant. Theia, as we've pictured it, a substantial world in its own right, had been on its collision course for some time. In the final hours, it would have loomed impossibly large in the proto-Earth's sky, no longer a distant point of light but a terrifying, approaching globe, perhaps visibly scarred and glowing from its own internal heat and recent smaller impacts. For the proto-Earth, still a molten or semi-molten sphere itself, largely undifferentiated, this was an appointment with destiny, a destiny written in the unforgiving language of gravity and momentum. The impact, when it came, would have been off-center, an oblique strike. This is crucial, as a direct, head-on collision would have had different consequences, perhaps shattering both bodies more completely or resulting in a more thorough mixing that doesn't quite fit the lunar evidence. An angled impact, however, is perfect for ejecting material into orbit and for imparting that all-important angular momentum to the Earth-Moon system. Imagine the moment of contact. Two planetary bodies, each with immense mass and traveling at cosmic velocities, likely tens of thousands of kilometers per hour relative to each other, slamming into one another. The energies involved are simply beyond human experience. It's not like a car crash or even an asteroid impact like the one that wiped out the dinosaurs. This is planet hitting planet. The shockwaves generated would have been incredible, propagating through both Theia and the proto-Earth at tremendous speeds, far faster than the speed of sound and rock. The leading edge of Theia would have plowed deep into the proto-Earth's mantle. Rock, under such extreme pressures and temperatures, ceases to behave like rock. It behaves like a fluid or even a gas. The interface between the two colliding worlds would have become a zone of unimaginable compression and heating. Temperatures would have skyrocketed to thousands, perhaps tens of thousands of degrees Celsius, hotter than the surface of the sun. Rock would have instantly vaporized, creating a rapidly expanding plume of superheated silicate gas. The sheer kinetic energy of Theia's motion would have been converted into heat and deformation. The proto-Earth would have recoiled, shuddered, its surface likely rippling like a struck gong, if a gong could be made of molten rock the size of a planet. A significant portion of Theia itself would have been utterly destroyed, its structure obliterated, its material mingling violently with the upper layers of the proto-Earth. Think of dropping a cannonball into a vat of thick treacle, but on a scale that defies terrestrial comparison, and with energies that make volcanoes look like tiny flickering candles. The material from both Theia and the proto-Earth, primarily their mantles, as Theia's iron core plunged deeper to merge with Earth's core, would have been ejected outwards. Not in a neat stream, but in a chaotic, incandescent spray of molten droplets, vaporized rock and larger, shattered fragments. This wasn't a clean, surgical strike. This was a messy, brutal, planet-scale demolition. The proto-Earth itself would have been catastrophically deformed. Its surface would have become a roiling ocean of magma, any pre-existing crust instantly obliterated. Its atmosphere, if it had one, would have been blown away, replaced by a temporary, searingly hot atmosphere of rock vapor. It's a vision of hell, a truly Dantean inferno on a planetary scale. The very definition of a bad day in the early solar system. You wouldn't want to have been anywhere nearby, unless your idea of a relaxing afternoon involves being vaporized and incorporated into a moon. The sound, if sound could have propagated in the near vacuum of space, which it can't, a lovely bit of stark cosmic reality that makes space horror movies particularly unsettling, your screams are truly silent, would have been deafening beyond comprehension. The flash of light from the impact would have been blinding, briefly outshining the young sun for any hypothetical observer in the solar system. And all of this happened relatively quickly. The main impact event, the actual collision and catastrophic disruption, would have unfolded over a matter of hours. The immediate aftermath, the settling of debris, the initial formation of the proto-lunar disk, would have taken a bit longer, but still astonishingly fast on geological timescales. It's hard to overstate the sheer violence. We talk about mountain-building events on Earth, or massive volcanic eruptions. These are geological whispers compared to the roar of the Theia impact. This event didn't just crack the crust. It fundamentally reset the geological clock for Earth, and it provided the raw, superheated ingredients for an entirely new celestial body. The proto-Earth, now significantly larger thanks to absorbing most of Theia, including its dense iron core, would have been left reeling, a glowing, molten sphere, ringed by a colossal disk of incandescent debris. It would have been unrecognizable from the world it was just hours before. Scarred, superheated, and spinning faster, it had survived, but it was forever changed. And in its fiery embrace, the seeds of its future companion, our moon, were sown. It's a terrifying image, this planetary demolition. Yet there's a strange, stark beauty to it. The universe, in its grand, impersonal way, engages in acts of creation that are inextricably linked with destruction. This wasn't an act of malice, it was physics. It was the chaotic dance of gravity and matter in a young, untamed solar system. And from this ultimate act of cosmic violence, something serene and enduring was about to be born. But first, that ring of fire and fury needed to cool and coalesce. The day the proto-Earth shattered was the day the moon began. The collision itself was an event of almost instantaneous, unimaginable violence. But what of the immediate aftermath? Theia was largely obliterated, its core sinking into the molten heart of the proto-Earth. A vast quantity of superheated rock, vapor, and debris, a mixture of Theia's mantle and the proto-Earth's upper layers, had been blasted into orbit. This wasn't a neat, tidy collection of pebbles. This was a seething, incandescent halo of cosmic wreckage, a truly hellish, glowing ring encircling the traumatized, newly reformed Earth. Let's try to visualize this, the moon's unlikely cradle. Imagine looking up from the surface of the still glowing, magma-covered Earth, a purely hypothetical viewpoint, as nothing could have survived there. The sky wouldn't have shown the familiar stars or a serene, silvery moon. Instead, it would have been dominated by a colossal, luminous band of fire and fury arching across the heavens. This proto-lunar disk, as scientists call it, would have been incredibly hot, thousands of degrees Celsius. It would have shone with its own internal light, a diffuse, angry red or brilliant orange, perhaps outshining the young sun itself in terms of immediate visual impact. This wasn't a solid ring like Saturn's icy structures. This was a dynamic, turbulent system. It would have been composed of molten rock droplets of various sizes, from tiny spherules to larger, kilometer-sized chunks of partially melted or resolidified debris, all swirling in a dense cloud of silicate vapor. Think of a blacksmith's forge, but scaled up to encompass an entire planet, with molten metal and glowing embers replaced by planetary guts. The sheer density of material would have been immense, far denser than Saturn's rings. The pressure and temperature within this disk would have been extreme. Close to the Earth, the innermost parts of the disk might have been so hot that rock remained in a gaseous state. Further out, as temperatures dropped slightly, molten droplets would have condensed from the vapor, like a fiery rain that never reached a surface, instead joining the swirling melee. Collisions within the disk would have been constant. Small particles would smash into larger ones, sometimes sticking, sometimes shattering each other, sometimes vaporizing each other anew. It was a chaotic mosh pit of incandescent rubble. This ring wouldn't have been static. It would have been rotating rapidly around the Earth, a consequence of the angular momentum imparted by Theia's oblique impact. And it would have been spreading out, constrained by Earth's gravity but also influenced by its own internal pressure and viscosity. The particles within it wouldn't have been on neat, circular orbits initially. Their paths would have been eccentric, crisscrossing, leading to that constant, furious bombardment and agglomeration. The Earth itself would have been profoundly affected by this nearby inferno. The sheer radiative heat from the disk would have kept Earth's surface molten for a considerable time. Any attempt by the planet to cool and form a solid crust would have been thwarted by this radiant furnace in its sky. It was a shared trauma, Earth and its nascent lunar material locked in a fiery embrace. And what of the smell? Purely speculative, of course, as no human nose could have endured it, but one can imagine the acrid stench of vaporized rock, sulfurous compounds, a primordial brimstone perfume on a planetary scale. A truly uninviting aroma, signaling a world still raw, still reeling from its catastrophic makeover. Not exactly the gentle, soothing scent of chamomile you might associate with bedtime. It's a stark contrast, isn't it? The serene, pale moon we see today, a beacon of calm in the night sky, was born from this maelstrom of fire and fury. This glowing, chaotic ring was its crucible. The conditions were so extreme that, as we've discussed, volatile elements, water, carbon compounds, anything that could easily turn to gas, would have been largely boiled away and lost to space. This is why the moon is so remarkably dry, so depleted in the building blocks of life as we know it. It was forged in an environment that was actively hostile to such delicate substances. Only the most refractory materials, those that can withstand incredibly high temperatures, like silicates and certain oxides, could have condensed and survived to form the bulk of the moon. The lifetime of this initial, superheated debris disk might have been surprisingly short in cosmic terms. While the accretion of the moon itself took longer, the initial phase of a dense, vapor-rich disk probably cooled and started to condense into larger bodies relatively quickly, perhaps within years or decades. The universe, even in its most destructive moods, is efficient. It doesn't like to leave a mess hanging around for too long if gravity can help tidy it up. So, when you look up at the moon tonight, try to overlay this image in your mind. Before it was a sphere, it was a ring. A ring not of ice and dust like Saturn's, but of fire, vapor, and molten rock. A raging, incandescent halo born from the collision of two worlds. It's a testament to the universe's ability to create beauty from chaos, order from unimaginable violence. Our moon didn't just pop into existence. It was smelted, refined, and forged in a cosmic furnace that wrapped the early Earth in a temporary, terrifying, but ultimately creative, embrace. This ring of fire and fury was the raw material, the violently prepared dough, from which our celestial companion was about to be kneaded into existence. The fiery, chaotic ring of debris, that incandescent halo encircling the traumatized proto-Earth, was not a permanent feature. The universe, for all its penchant for dramatic explosions and cosmic smash-ups, also possesses an inexorable drive towards, well, if not exactly tidiness, then at least a clumping together of things, thanks to our old friend, gravity. That seething band of molten rock, vapor, and shattered planetary remnants was the raw material, the cosmic junkyard from which our moon would slowly, perhaps even painfully, piece itself together. This wasn't an instantaneous assembly, it was a process, an accretionary ballet played out in the aftermath of planetary violence. Imagine the scene within that turbulent disk. Initially, it was a dense soup of silicate vapor and tiny molten droplets. As the disk began to cool slightly, and cool is a relative term here, we're still talking about temperatures that would make a blast furnace feel like a refreshing spring breeze, these vapors started to condense into larger particles. Tiny pebbles of resolidified rock began to form, swirling amidst the still hot gas. These newly formed pebbles, along with larger fragments ejected directly from the impact, began to collide. Not with the cataclysmic force of the initial Theia impact, but with enough energy for them to sometimes stick together. Gravity, even between small objects, exerts a pull, and in a crowded disk, encounters were frequent. It was a cosmic game of sticky billiards. A small rock bumps into another, they merge. This slightly larger rock then has a bit more gravity, making it a slightly more effective collector of other small rocks. This process, known as accretion, is fundamental to how planets and moons form. It's a runaway effect. The bigger an object gets, the more effectively it can gravitationally attract and sweep up smaller material in its vicinity. So, within this protolunar disk, certain regions, perhaps slightly denser than others, or where a few larger initial fragments happen to be, would have started to grow more rapidly. These became the seeds of the protomoon, or perhaps multiple protomoons initially. Computer simulations suggest that within this disk, numerous moonlets, perhaps dozens or even hundreds of them, ranging in size from large boulders to small mountains, could have formed relatively quickly, possibly within a few years to a few decades. The disk was a rich feeding ground. It wasn't a gentle, leisurely process. These moonlets would have been orbiting the Earth, their paths still somewhat chaotic, their surfaces still incredibly hot, likely molten or very nearly so. Then the next phase of the drama began. a period of moonlet mergers. These smaller, newly formed bodies would have continued to interact gravitationally. Their orbits would have crossed. And when they met, they didn't just politely nod and pass by. They collided and merged, forming even larger bodies. It was a period of celestial cannibalism, where the bigger moonlets grew by consuming their smaller siblings. Each such merger would have been a significant event, releasing more heat, keeping the growing proto-moon in a molten or partially molten state. This process continued, with larger and larger bodies dominating, sweeping up the remaining debris in smaller moonlets. Eventually, through this hierarchical series of collisions and mergers, one body would have grown significantly larger than all the others. This dominant survivor, this heavyweight champion of the proto-lunar disk, was destined to become our moon. The timescale for this main phase of accretion from a disk of debris to a mostly assembled moon is thought to be surprisingly short in cosmic terms. Estimates vary, but it could have been as little as a few months, or perhaps up to a century. Not millions of years, but a rapid, almost frantic construction project carried out in the immediate fiery aftermath of the giant impact. The universe, it seems, doesn't like to waste good building material. As the moon grew, its own gravity would have shaped it into a sphere. Its surface would have been a roiling ocean of magma, constantly bombarded by the remaining debris from the disk. This is the magma ocean we spoke of earlier, the evidence for which is found in those anorthositic rocks brought back by the Apollo missions. These lighter rocks crystallized from the cooling magma ocean and floated to the surface, forming the moon's primordial crust, the very highlands we can still see today as the brighter, more heavily cratered regions. Even after the bulk of the moon had formed, the bombardment wouldn't have stopped immediately. The early solar system was still a messy place. The moon and the Earth would have continued to be pelted by smaller asteroids and comets for hundreds of millions of years, a period known as the Late Heavy Bombardment. This is what created the vast majority of the craters we see on the moon's ancient surface, a pockmarked testament to its violent youth. The moon, lacking an atmosphere or geological activity to erase these scars, wears its history on its face. Earth got hit just as much, if not more, but our planet's active geology, weathering, and erosion have wiped away most of the evidence, like a constantly self-cleaning slate. The moon, in its stark stillness, remembers. So, our radiant sphere, the one that inspires poetry and lights up our nights, wasn't born in gentle starlight. It was assembled piece by piece from the incandescent wreckage of a planetary collision, a chaotic, violent process of accretion and merger, all taking place within a swirling, superheated disk of cosmic rubble. It's a far cry from the serene image we usually associate with it. It's a story of transformation, from shattered remnants to a cohesive whole, from a ring of fire and fury to the pale, silent sentinel that now graces our sky. It's a reminder that even in the most extreme conditions, gravity and time can sculpt wonders. And sometimes, to get something beautiful and enduring, you first have to smash things up quite spectacularly. The universe, it seems, is a fan of dramatic entrances. So, our moon has been assembled, pieced together from the fiery detritus of a planetary cataclysm. It's no longer a ring of incandescent rubble, but a mostly formed sphere, albeit one still glowing with primordial heat and nursing a vast magma ocean. Now, the critical question, does this dramatic, violent, and frankly rather messy birth story, the giant impact hypothesis, actually hold up under scrutiny? Does it provide a convincing alibi for all the moon's peculiar characteristics, those little quirks that stumped all the previous, more sedate theories? The answer, much to the satisfaction of cosmic detectives and insomniacs pondering lunar origins, is a resounding, if slightly singed, yes. This catastrophic collision, it turns out, elegantly explains why our moon is the way it is, with its oddly light heart and its familiar yet distinctly different face. Let's revisit those key pieces of evidence, those forensic clues from the lunar crime scene, and see how the giant impact hypothesis provides the perfect cosmic alibi, or at least the most compelling one we have to date. First, the moon's small iron core, its apparent aversion to heavy metals. Remember how the co-formation theory stumbled here, unable to explain why Earth got all the iron if they formed side by side? The giant impact provides a beautifully brutal solution. When Theia, that Mars-sized protoplanet, slammed into the proto-Earth, the collision was so energetic that the dense iron core of Theia, and any iron from the impacted part of Earth's mantle, wasn't just scattered willy-nilly. Instead, under the influence of gravity and the immense pressures involved, Theia's core is thought to have largely merged with the proto-Earth's own growing core. It sank through the molten silicate material of the combined planetary mess, adding its metallic payload to Earth's heart. What was ejected into orbit to form the moon, then, was primarily the lighter, silicate-rich mantle material from both Theia and the Proto-Earth. This material is naturally much lower in iron content. So, the Moon, accreting from this iron-depleted debris disk, naturally ended up with only a tiny iron core of its own, if any significant one at all from that event. It's like a cosmic siphoning process. The collision skimmed off the rocky froth, leaving the dense dregs to settle within Earth. Earth got the lion's share of the iron and the Moon got the leftovers. A bit unfair to the Moon, perhaps, but perfectly consistent with what we observe. No more mystery about the missing iron. It simply wasn't in the recipe for the Moon's building blocks in the first place, having been gravitationally sequestered deep within the Earth. Next, the Moon's striking lack of volatile elements, water, sodium, potassium, and the like. Why is our Moon so cosmically desiccated, so thoroughly baked? Again, the giant impact provides a fiery explanation. The sheer energy of the collision, as we've discussed, would have heated the ejected material to thousands of degrees Celsius. Much of it would have been vaporized. In such extreme temperatures, volatile substances, which have low boiling points, simply wouldn't have condensed into the moon-forming disk in significant quantities. They would have remained as gas and been blown away by the solar wind or otherwise lost to space. The Moon, therefore, was born bone-dry, not because it formed in an arid part of the solar system, but because it was forged in an incredibly hot crucible that boiled off its potential water and other easily vaporized components. It's like trying to make a snowman in a blast furnace. You're not going to have much luck. Then there's the evidence for an ancient lunar magma ocean. Those anorthositic highlands on the Moon, composed of lighter rocks that floated to the top of a molten sea, cry out for an incredibly energetic formation event. A gentle co-accretion or a cool capture wouldn't provide nearly enough heat to melt the entire outer portion of a moon-sized body. But the giant impact? Absolutely. The energy released by the collision itself, followed by the rapid accretion of hot debris to form the Moon, would have been more than sufficient to create a deep, global ocean of molten rock. The Moon literally started its life as a glowing ball of lava, slowly cooling and solidifying from the outside in. The magma ocean isn't just consistent with the giant impact. It's practically a predicted consequence. What about the Earth-Moon system's high angular momentum? That excessive spin energy that puzzled earlier theories? An oblique off-center impact by a Mars-sized body is an extremely efficient way to generate just such a high angular momentum. Imagine hitting a billiard ball not quite in the center. It doesn't just move forward, it also spins. Scale that up to planetary dimensions, and you have the proto-Earth and the ejected debris cloud set into rapid rotation and orbit. The physics of such a glancing blow naturally produces a system with lots of spin, neatly explaining why our day was likely much shorter in the past and why the Moon orbits as it does. And finally, those all-important oxygen isotopes. The fact that Earth and Moon rocks have virtually identical oxygen isotope fingerprints was a major stumbling block for theories that proposed the Moon formed elsewhere, like capture, or didn't involve thorough mixing, like some versions of co-formation. The giant impact handles this with aplomb. If the Moon is formed primarily from material ejected from Earth's mantle, mixed with material from Theia's mantle, which, having formed in a similar solar system neighborhood, likely had similar isotopes, or the impact was so violent it homogenized everything, then the isotopic match is expected. The Moon is, in a very real sense, made of processed Earth stuff along with Theia stuff. They share a common chemical heritage because they were literally, catastrophically, blended together. So you see, the giant impact hypothesis isn't just a dramatic story, it's a powerful scientific model that ticks off the checklist of lunar mysteries with remarkable success. It explains the iron, the dryness, the heat, the spin, and the chemistry. It's like a detective who finally finds the one scenario that makes all the contradictory witness statements and forensic evidence fall neatly into place. It was a messy crime scene, no doubt, but the story it tells is coherent. Our Moon, with all its beautiful, serene oddities, is the natural, expected outcome of a truly monumental cosmic collision. The alibi holds. Or at least it's the best one we've got, providing a framework so robust that most lunar scientists can, quite literally, sleep on it. The giant impact hypothesis, with its grand, sweeping narrative of planetary collision and lunar rebirth, provides a remarkably compelling explanation for the Moon's major characteristics. It's like a beautifully constructed cosmic alibi, as we've said, fitting the big pieces of the puzzle: the iron deficiency, the volatile depletion, the magma ocean, the high angular momentum, and the isotopic similarities, with an almost unsettling neatness. But science, in its relentless pursuit of understanding, and its occasional delight in poking holes in even the most elegant theories, doesn't just rest on the broad strokes. The devil, as they say, is often in the details. And it's in these nitty-gritty details, these finer points of evidence and modeling, that the true strength and also the ongoing refinement of the giant impact hypothesis really shines. It's not just a good story, it's a story that has been rigorously tested and prodded by decades of sophisticated computer simulations. These simulations are like virtual cosmic laboratories where scientists can tweak the parameters, the mass of Theia, the angle of impact, the velocity of the collision, and watch what happens. They can model the ejection of debris, the formation of the disk, and the subsequent accretion of the moon. And what they find is that a Mars-sized impactor, striking the proto-Earth at an oblique angle, consistently produces outcomes that look remarkably like our Earth-Moon system. For instance, these simulations can track where the material that forms the moon originates from. Early models often suggested the moon should be predominantly made of material from Theia, the impactor. This created a slight tension with the oxygen isotope data, which suggested a very strong Earth-like signature. If Theia came from a slightly different part of the solar system, it might have had a slightly different isotopic fingerprint. So, why is the moon so Earth-like? More recent, higher-resolution simulations and refined understandings of planetary mixing in such violent impacts have shown that a significant portion of the material in the disk can indeed come from Earth's mantle, or that the impact was so energetic that the vaporized material from Earth and Theia mixed incredibly thoroughly before condensing. This helps to reconcile the Theia impact scenario with the strong terrestrial isotopic signature of the moon. The cosmic blender was apparently very efficient. Then there's the orbital dance of the Earth and Moon. Our moon is currently receding from Earth at a rate of about 3.8 centimeters per year, roughly the speed at which your fingernails grow. This is due to tidal forces. Earth's rotation is slowing down, and to conserve angular momentum in the system, the moon moves further away into a higher orbit. If you run this process backwards in time, it implies the moon was much closer to Earth in the distant past. The giant impact hypothesis, with its scenario of the moon forming from a debris disk relatively close to Earth, is perfectly consistent with this. In fact, the initial Earth-Moon distance after the moon's formation was likely only about 20,000 to 30,000 kilometers, compared to the nearly 400,000 kilometers today. Imagine the moon looming enormous in the primordial sky, perhaps 10 to 20 times larger in appearance than it is now. A truly breathtaking and probably somewhat terrifying sight. The tides on a molten Earth would have been colossal, hundreds of meters high, a sloshing planetary scale readjustment. The details of the moon's composition also offer further support. For example, the moon is enriched in certain refractory elements, those that condense at high temperatures, compared to Earth, which is consistent with it forming from a very hot, vaporized disk. Conversely, it's depleted in more volatile elements, not just water but also things like zinc, tin, and lead, to a greater extent than can be easily explained by other theories. The extreme heat of the impact provides a natural mechanism for this selective elemental distillation. Scientists even look for subtle isotopic signatures of other elements, like tungsten. Tungsten isotopes can provide clues about the timing of core formation in planetary bodies. Studies of terrestrial and lunar tungsten isotopes are consistent with the giant impact scenario, suggesting that the impact happened after Earth's core had largely formed, and that Theia's core did indeed merge with Earth's. It's like finding a tiny, almost invisible fingerprint at the crime scene that further corroborates the main suspect's story. However, it's important to note that the giant impact hypothesis isn't a completely settled, case-closed affair with no remaining questions. Science is always a process of refinement. For example, some models still struggle to get the exact isotopic match for all elements perfectly right while also producing a moon of the correct mass and an Earth with the correct rotation period. Some researchers have proposed variations on the theme. Perhaps Theia was larger or smaller or hit faster. Perhaps there were multiple, smaller impacts that collectively contributed to the moon-forming disk, rather than one single giant impactor, though this is a less favored idea currently. Some recent models even explore the idea of a much more energetic impact that created a vast, donut-shaped structure of vaporized rock called a synestia, from which both the Earth and Moon then condensed. This is cutting-edge stuff, pushing the boundaries of our understanding. These ongoing investigations and debates don't necessarily mean the core idea of a giant impact is wrong. Rather, they reflect the healthy, dynamic nature of science. Scientists are constantly trying to fine-tune the model, to resolve lingering discrepancies, and to explore the full range of possibilities within the giant impact framework. It's like having a very detailed suspect profile, and now you're trying to determine the exact shade of their eyes or the precise length of their alibi. But the overwhelming consensus is that a giant impact, in some form, is the best explanation we have for the origin of our moon. It's the theory that best fits the multitude of observational constraints, from the moon's bulk properties to its detailed geochemistry and its orbital dynamics. The nitty-gritty details, far from undermining it, have largely served to strengthen its plausibility, even as they reveal new layers of complexity and new avenues for research. It's a testament to a good scientific theory that it can not only explain what we already know but also make predictions and stimulate further investigation into the finer details. And in the case of the moon's birth, the details paint a consistent picture of a violent past leading to our serene present. So, we've journeyed through the dramatic tale of the giant impact hypothesis. We've seen a Mars-sized protoplanet named Theia meet a cataclysmic end, its collision with the young Earth flinging a maelstrom of incandescent debris into orbit, debris that eventually coalesced into our familiar, cratered companion. It's a story that elegantly explains the moon's missing iron, its baked-dry nature, its molten past, and the peculiar dance it shares with Earth. Feels complete. Almost too complete, perhaps. Like a mystery novel where the detective ties up every loose end with a flourish, leaving the reader satisfied, yet perhaps a tiny bit suspicious that real life is rarely so neat. And indeed, in the grand, ongoing cosmic investigation that is science, the file on the moon's origin, while largely dominated by the giant impact hypothesis, isn't quite slammed shut, locked away, and gathering dust in the archives of settled facts. While it's by far the most widely accepted and best supported theory, the scientific process is one of perpetual refinement, of constant questioning, and of an almost insatiable curiosity that keeps poking and prodding even at its most cherished explanations. The universe, after all, has a habit of throwing curveballs when we least expect them. It delights in the but have you considered this moment? Think of it less as a finished manuscript and more as a living document, a theory that continues to evolve as new data comes in, as computational models become more sophisticated, and as clever minds devise new ways to test its predictions. Scientists are, by nature, professional skeptics. Even when a theory works beautifully, they're always looking for the cracks, the inconsistencies, the subtle anomalies that might hint at something deeper, something even more wondrous, or perhaps even more unsettlingly complex. For instance, while the oxygen isotope similarity between Earth and Moon is a strong pillar of the giant impact theory, some other isotopic systems, like those of titanium or chromium, show subtle differences that are still being actively researched and debated. Are these differences relics of Theia's original composition, not fully erased by the impact? Or do they point to complexities in the mixing processes within the protolunar disk? Or perhaps they hint at later additions of material to Earth or the Moon? These are the kinds of detailed questions that keep lunar geochemists happily employed and occasionally pulling their hair out. The universe isn't always forthcoming with simple answers, even when you ask very politely with a mass spectrometer. Then there's the ongoing quest to refine the exact nature of Theia and the impact itself. How big was Theia really? Was it truly Mars-sized, or perhaps a bit larger, or even smaller but hitting at a higher velocity? What was its composition? Did it come from the same neighborhood as Earth, or was it an immigrant from a different part of the solar system, bringing its own chemical baggage? As we discussed, some recent simulations are exploring scenarios like the Synestia model, where the impact was so energetic it created a massive, donut-shaped structure of vaporized rock from which both Earth and Moon condensed. This is still within the giant impact family of theories, but it pushes the boundaries of what we thought was possible, envisioning an even more extreme and exotic formation environment. The search for direct evidence of Theia itself is another tantalizing, if perhaps ultimately quixotic, quest. Could there be tiny isotopic traces of Theia's unique signature still lurking deep within Earth's mantle? Or perhaps in specific lunar rocks that somehow preserved a less mixed sample of the impactor? Finding such a smoking gun would be an incredible validation, but the immense mixing and geological processing that both Earth and Moon have undergone over 4.5 billion years makes this an incredibly challenging task. It's like trying to find a single grain of sand from a specific long-vanished beach, now scattered across an entire continent. And what if, just what if, a completely new piece of evidence emerges? Perhaps from future, even more sophisticated lunar sample return missions, or from observations of moon-forming disks around distant exoplanets, if we can ever see them in enough detail. Science must always be prepared for the unexpected, for the observation that doesn't quite fit, the one that forces a re-evaluation of even the most entrenched ideas. That's the beauty and the terror of the scientific endeavor. It's a never-ending story, constantly being revised and updated. This doesn't mean you should lose sleep worrying that the giant impact hypothesis is about to be overturned tomorrow, replaced by a theory involving, say, cosmic space goats headbutting the moon into existence. The weight of evidence supporting a cataclysmic impact origin for the moon is immense, but it does mean that the story isn't static. It's a vibrant field of research, full of passionate debate and exciting new discoveries. It's a humbling lesson, really. Even for something as seemingly familiar as our own moon, something that has hung in our skies for all of human history, the complete truth of its origin is still a work in progress, a masterpiece that scientists are meticulously, patiently, and sometimes frustratingly trying to complete. The universe doesn't give up its secrets easily. It makes us work for them, challenging our ingenuity, our technology, and our capacity for both rigorous logic and wild imagination. So, as you drift off, remember that the story of the moon's birth, while largely understood through the lens of a colossal impact, is still a tale with a few tantalizingly blank pages, a few footnotes yet to be written. The cosmic investigation continues. And that, in itself, is a wonderfully unsettling, yet ultimately reassuring thought. It means there are still mysteries to unravel, still wonders to discover, even in our own celestial backyard. The universe, as always, keeps us guessing, and perhaps that's part of its enduring, sleep-inducing charm. It's too vast, too complex, too wonderfully strange to ever be fully, finally, boringly figured out. And so, we find ourselves at the end of this particular cosmic journey, tracing the epic and often rather messy saga of our moon's birth. We've sifted through the cosmic crime scene, examined the discarded theories, the Earth spinning off a child, the kidnapped celestial wanderer, the quietly forming twin, and arrived at the current reigning champion, the giant impact hypothesis. A tale of a phantom planet named Theia, a cataclysmic collision of unimaginable violence, and a moon forged from the fiery, incandescent wreckage. It's quite a story, isn't it? Our serene, silvery moon, the gentle lamplight of our nights, the inspiration for poets and lovers, the steady hand guiding our tides, born from an event so destructive it would make any Hollywood disaster movie look like a minor fender bender. There's a profound irony there, a cosmic joke almost. The epitome of tranquility in our sky is the child of utter chaos. It's as if the universe, with its characteristically dark sense of humor, decided to show us that beauty can, and often does, arise from the most brutal of origins. Think about it as you lie there, nestled in your terrestrial comforts. That pale disk hanging in the velvet black, so seemingly placid, so ancient, so lunar. It's a constant, silent reminder of a day 4.5 billion years ago, when our young Earth was dealt a body blow of planetary proportions. A day when another world died so that our moon could be born, and so that Earth itself could be fundamentally reshaped into the planet we know today, with its particular tilt, its spin rate, and its large, stabilizing companion. Perhaps without that ancient violence, without Theia's sacrifice, this habitable little rock we call home might not be so habitable. Maybe life itself, in all its fragile, improbable glory, owes a debt of gratitude to that catastrophic smash-up. The universe works in mysterious and often rather alarming ways. The moon, then, is more than just a pretty nightlight. It's a scar, a memento, a beautifully sculpted piece of shrapnel from our solar system's rough-and-tumble youth. It carries the chemical fingerprints of both its parents, the proto-Earth and the doomed Theia, blended together in a fiery crucible. Its ancient, cratered face tells a story of relentless bombardment, a history book written in impact scars, largely unedited by the geological processes that constantly resurface our own dynamic planet. There's a strange comfort in this, perhaps. Our daily anxieties, our little human dramas, the things that keep us tossing and turning at night, they shrink into almost comical insignificance when juxtaposed with the sheer scale and violence of the moon's birth. Worried about that awkward conversation at work? Try to imagine a Mars-sized planet slamming into yours. Suddenly, sending that email doesn't seem quite so terrifying. It's the universe's way of saying, "Relax, kid. I've seen worse. Much, much worse." And from it came that, gesturing with a metaphorical cosmic thumb towards the Serene Moon. And yet, despite understanding its violent origins, despite knowing it's a geologically dead world, a desolate landscape of dust and rock, the moon retains its magic, its allure. It still pulls at our oceans, still inspires wonder, still serves as that familiar anchor in the ever-shifting patterns of the night sky. Knowing its story doesn't diminish its beauty. If anything, it adds a layer of profound and perhaps slightly unsettling depth. It's a beauty born of cosmic indifference, an accidental splendor arising from the chaotic laws of physics playing out on a grand scale. The universe wasn't trying to make something beautiful for us to gaze upon. It was just doing its thing. And this serene silver orb is one of the byproducts. So, as you prepare to drift off into the realm of dreams, let the story of the moon's formation settle in your mind. Let it be a reminder of the immense, ancient, and often terrifyingly powerful forces that have shaped our world and our celestial neighborhood. Our peaceful sky belies a violent past. And in that juxtaposition, there's a kind of peace to be found. The peace of acceptance, perhaps, of our small place in a vast, indifferent, yet occasionally spectacular cosmos. The moon, our violent moon, now watches over your peaceful sky. A silent testament to destruction, creation, and the enduring, often ironic beauty of the universe. And so, little speck of stardust, voyager on this tiny blue marble, it is time. The grand, tumultuous story of our moon's fiery birth has drawn to a close for tonight. The echoes of colliding worlds, of vaporized rock and incandescent rings, now fade into the vast, indifferent silence of the cosmos. Let them fade. Theia is long gone, a ghost planet absorbed into the very fabric of our Earth, her sacrifice immortalized in the silver glow that might even now be filtering through your window. The magma oceans have cooled. The relentless bombardment has dwindled to a mere sprinkle of cosmic dust. What remains is that serene, pockmarked face, a steadfast companion on our journey through the endless night. Perhaps tomorrow you'll look up at it, that familiar lunar disk, and see it with new eyes, not just as a light, but as a survivor, a testament to cosmic resilience, a beautifully scarred relic of a truly terrible yet world-defining day. Perhaps you'll feel a strange kinship with it, another entity sculpted by forces far beyond its control. But for now, let that be. Let the sheer, mind-boggling scale of it all, the casual violence and the accidental beauty gently cradle your mind. Your worries, your stresses, the insistent hum of your daily life, they are but fleeting whispers in the grand amphitheater of cosmic time. The universe, with its penchant for cataclysm and its unhurried eons, will still be there when you wake. It doesn't need you to solve its mysteries tonight. It doesn't need you to fret about its vastness or its indifference. All it asks is that you rest, that you allow the gentle gravity of sleep to pull you down into the soft darkness. Like a tiny moonlet, spiraling gently towards a peaceful orbit. Surrender to the quiet. The universe is vast and yes, occasionally quite brutal. But here, in this moment, in the safe haven of your bed, you are secure. The cosmic dramas can wait. Breathe deeply. And sleep. Sleep, knowing that even from the most unimaginable chaos, something beautiful and enduring can arise. Sweet dreams, cosmic traveler. You are, after all, made of the same stuff as stars, and the debris of shattered worlds. And that, in itself, is a rather wonderful, if slightly unsettling lullaby.